f is a function of a vector v that outputs a scalar. Specifically, f is equal to the norm of v, the input, squared. So here's what we're going to do. We're going to prove that f of v, or rather the norm of v squared, is equal to this very scary looking expression. Alright, what's going on here? Well, here's the thing. Whenever we have a function in one dimension, or mapping R to R, you can come up with a Taylor approximation at some point. Now, this approximation allows you to predict what the value of points near the center of your approximation are going to be. For example, I can have a first order linear approximation, or a second order parabolic approximation, or even a fourth order approximation, and eventually I can get an approximation so good it's basically perfect over a considerable range. So, of course, as you know, the formula for one of these approximations is just f of x at any point is equal to f of c, where c is our center, plus f prime of c multiplied by x minus c, plus 1/2 f prime prime of c, x minus c squared, and so on and so forth. Like plus 1/6 f triple prime of c, x minus c cubed, and so on and so forth. Alright, so can we extend that to multiple dimensions? Yes, we can. Let's imagine something in 2 dimensions. Something mapping R2 to R, which is expressed as a surface. So let's say we have this surface here, which is gonna, I'm gonna make it look like a mountain. So that means I'm gonna have it peak over here before coming down. Okay, yeah. We're golden. Okay. Okay, so we have this nice looking hill over here, right? And here's what we're going to do. So, at the top of this hill, can we do a Taylor approximation sort thing? Yes, we can. Not with another surface, actually, but with a line. So what we can do is we can start with that nice looking linear approximation, then get to quadratic, and so on and so forth. And the way we do this is using a directional derivative, because, I mean, you can't just approximate the entire function over a specific circular region. You have to be approximating the function from one center in one direction, which means that you're going to have to be taking the directional derivative at that point, essentially taking the cross section of the function in that direction and then treating it like a normal Taylor expansion. So, in the case of this guy right over here, a multivariable function can be written as f of v naught plus f prime of v naught, which is actually the gradient, which I'll express as d, f at v naught multiplied by v minus v naught technically this is vector 2, I'm not sure why I said technically, plus, note that this is a matrix, oh wait, oh I'm done, sorry, this is the direction of our derivative, going crazy, plus 1/2 the second derivative, which happens to be a matrix, then the third derivative, which is a rank 3 tensor, and so on and so forth. And you might be thinking, how do we reduce all of this messiness to this? Well, it's pretty simple. First things first, we observe this guy right here, which tells us that our center should probably be equal to 0. And if our center is equal to 0, that simplifies a lot of things, and also that explains why this is just v comma v instead of v minus something comma v minus something. So let's say this is the 0 vector. So our approximation is centered at 0. Okay, good. So now we have this plus dot dot dot. Now here's the special thing. What happens when we write this out? Well, if v has I components, let's say, this is just the square of the square root of v1 squared plus v2 squared plus da 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 plus vi squared. And so that means the square root and the square cancel out. Nice. Okay, and now that that's done, what is this vector going to look like? Well, this is just the gradient of f dot v. So that should make enough sense. So in this case, it's going to be the gradient of f at 0 dot v. So the gradient of f is just going to be partial f partial v1 partial f partial v2 dot 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 partial f partial vi dot v1 v2 dot 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 vi. But first, let's focus on getting rid of as many things as possible, because this is supposed to be reduced to one term. First things first, f of 0, that's very obviously going to be 0, right? Because with the 0 vector, every component is 0, right? Which means that this is just going to be 0 squared. So we're going to take this guy out. All right. Second thing, how do we get rid of this guy? Because that's like an infinite sum and stuff. We don't want that. So how do we get rid of this? Well, very simple answer. Here's the thing. What does the Hessian or the matrix of all the sectors even look like? Well, that's going to be what? The first derivative, well, no, let's get straight to the second derivative. So this is going to look like partial f, partial v1, v1, partial squared f. Okay. Partial squared f, partial v1, partial v2, dot, 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 partial squared f, partial v1, partial vi, partial squared f, partial v2, v1, partial squared f, partial v2, should have put two of these, partial squared f, partial vi, and finally, partial squared f, partial vi, partial v1, Okay, this looks good. Now, here's what we're thinking. First of all, partial f, partial k for any given k. Well, v1 squared is going to go to 0 when we take the derivative by k. So is v2. Everything's going to go to 0 except the specific term vk squared, which is going to go to 2vk. Which means that this is always going to be 2vk. So, what's partial squared f partial vj partial vk? Well, that's partial f partial vj of 2vk. So that means that it's going to be 2 if j is equal to k, and it's going to be 0 if not. Which means this is going to be 2 across the diagonal, and since the indices are different everywhere else, a big fat 0. Boom. Great. Which makes this just equal to the 2 times the identity vector in I dimensions. Alright. So, what does this mean? Well, that means that since this is totally independent of v, that means that the third derivative of f, the rank 3 tensor, is going to be a 0 tensor. Same thing for everything succeeding it, which means that all of this goes to nil, which means it's just these two. It's just the two of us. Alright, and so now, how do we assassinate the final term? This guy, right here. Ew, what's this buildup?
What is the topic? Assassination of a complex analysis?
No, we're just making sure all of the terms are peacefully eliminated.
Or peacefully killed.
Sus. Okay. Okay, I'll need to wash this marker. Not sure what this buildup is. Okay, let's not concern ourselves with this for now. So, how do we assassinate this term, essentially? Well, here's the thing. Partial f partial v1 is equal to what? Wait a second. Oh. So, as we know, this is just 2v1, 2v2, 2vk, vi. But here's the thing, right? Here's the thing. v1 is currently going to be equal to 0, since we're plugging in the 0 vector into the gradient. This is 0. Same thing with this. Same thing with this. And keep in mind, these are actually components of the vector we plug in, not the 0 vector. But it doesn't even matter, because this is just going to be equal to 0. Which means that we've assassinated the final term, and we've managed to reduce everything to our desired half times the Hessian at 0 in the direction of v, reducing the expression for the Taylor expansion of a multivariable function.